per recording. Thanks, Jessica. Selena, so we can't use the triangle in the homework for all the problems under it. I guess I misunderstood the way it was presented. Just use different operators. Operate. That sounds like quantum mechanics. Okay, I don't know what you mean by operators, but yeah. So Selena, so if you're given a 45, so if I asked you what sine of 30 is, you would have to, if you haven't memorized this yet, you would have to draw your 30, 60, 90 triangle, and you would have to write the label. You'd have to say that, okay, this is the ratio of the legs is 1 to square root of 3 to 2, and then sine is opposite over adjacent, opposite over hypotenuse, so that's 1 over 2, so on and so forth. And you would have to use a different triangle if you were asked what is sine of 45. And draw it like this, right? Now you have to use these different ratios. And so we've done this before, right? 1 square root of 2, sine is 1 over square root of 2. So yeah, so you have to generally use a different triangle. But in theory, you only need to know the sine of these very popular, what I would call popular angles, 30, 45, 60, 90, 180, 270. All these intermediate values, you don't need to worry about them. In fact, it's very hard to compute these intermediate values without using a very precise graph, either if you graphed or using a protractor or just using a computer. So really all you should be expected to know is the sine of these popular angles. And for that, you only need these two triangles. Okay. Leanne said, the answer, yes, Leanne, you're right. The answer will change.
It'll change on different triangles? Like,
if the angles are different.
If the angles are different, okay.
Yeah, so so that's a good point. So if I can have a huge, I'll draw a tiny triangle. That's a 45, 40. Oh, that didn't. Okay, you see this little tiny itty bitty triangle, 45, 45, 90 triangle. And I can draw a huge triangle. That's also 45, 45, 90. And the sine of this angle is going to be the same as the sine of this tiny angle. It's not, I shouldn't even say tiny angle because it's the same angle, right? So the triangles can be different in size, but the angles have to be the same. Does that make sense? So we're going to talk about geometry next week, and these are similar triangles because the ratios of all the legs are the same. So yeah, the triangle can be different, but not really, in the sense, the triangle can be scaled up and scaled down if you multiply all the legs by the same number. Technically you don't have the same triangle, but really it is the same triangle because the ratios of the legs is preserved. Okay, so Lena says she understands. But okay, thanks for these questions. This is what I like. This is what I want the beginning of each lecture to be like, when people have questions and we can clarify. So this is actually very good. Lily, you have asked me privately, people can't see this in the chat, but you said, are the sides always 1, 1? And yes, because we learned it with X. Okay, Lily, let's talk after the lecture. It has nothing to do with, oh, you learned it with that. Okay, so some of you might see, sorry, so people could not see Lily's comment because she privately sent it to me. But people might have seen this. This is the same exact statement as, square root 2, 1, 1. This is exactly the same thing. This is just a bit more general because X here can be any number. But note that the sine of 45 here is the same thing as the sine of 45 here, if this is a 45, 45, 90 triangle up here. Because look, sine here is X divided by X square root 2, and the X's cancel. So you're left with this, which is the same thing that we would get from this. I didn't want to confound things by adding these, X's, but yeah, that's the same exact statement. Okay, and Selena, you've also asked, so in the homework I need to make you don't really need to make your own triangle with each problem. Okay, sure. I mean, if you want to, if you haven't memorized, I guess to answer your question, yes. But on the homework, you should only need those two triangles, 45, 45, 90, and 30, 60, 90. Okay, let's get on with the sort of the main content. So this is actually great because we've already summarized what we talked about yesterday. And what we talked about was sine for values above 90 and below 90, right? So the first day, day one of this, we found that we only talked about this little bit up till 90 degrees. And we found that sine behaves, I'll use a different color. We found that sine behaves like this. It goes up in an arc. We found that cosine on the first day behaves like this. It goes down. And we found that tangent behaves altogether differently, and it goes up and up and up, right? Like that. And yesterday we generalized, right? We extended beyond 90 degrees. And if we were to look at where we are on a different sort of plot, from here to here, that is 90 degrees. And that is what we talked about on the first day. Yesterday, we went beyond, right? We crossed this line here. By the way, I should have been more clear in saying that you always start measuring. This is where this line refers to where theta equals 0. And the convention is to measure positive theta for counterclockwise rotation. So it's not like a clock. And this is just something else to get used to. Counterclockwise rotation is the positive angle by convention, okay? So we started getting into answering questions like, what is the sine of 120 degrees? What is the sine of, all these intermediate things? And then we eventually said, what is the sine of 180 degrees? And then we went even further into this quadrant and into this quadrant, and so on and so we went all the way around the unit circle, and then we ended where we started, right? And then we found that everything repeats itself. Okay, so what was the big picture? What did we really find? Well, we found that sine for, say, 120, we found that it is positive. And we found that sine here is positive. In fact, the sine of 120 we found is equal to the sine of 60, right? Isn't that what we found? And when we graphed it, we indeed found that there was the symmetry here for this quadrant. See this quadrant here? Between 90 and 180 degrees, sine repeats itself, right? So for, here's the point 120, right? And it takes on the same value, see, same value as when sine was 60. So sine repeats itself. On the other hand, we found that cosine does not repeat itself. Cosine, right? We found that the cosine of 120, should use a different color. We found that the cosine of 120 is equal to the minus cosine of 60. And this appeared graphically because this graph here went below the axis. So cosine is not repeating itself. But then in this quadrant, right, as we ventured further, here we found that sine, okay, again, I'm confusing the colors. Here we found that sine, like say sine of, I don't know, 300 degrees. We found that sine of 300 degrees is negative sine 30 degrees. And that became visible by the fact that sine goes negative here, right? And here's the 0.270. And on the other hand, cosine repeats, this is where cosine starts repeating itself. So cosine of 300 was equal to cosine 120. And indeed, cosine starts repeating itself in this region. See, cosine of, here's where, sorry, I'm in the wrong quadrant. Sorry, people. I'm in the wrong, okay. 210, I meant 210, sorry. Thanks, Aditya. Yeah, sorry. Okay, I meant 210 here. 210. Anyway, you get the point, right? That cosine repeats itself in the third quadrant, and then it goes back up, and then sine repeats itself in the fourth quadrant. So I feel like a lot of this was hand waving. I was like, okay, this is just the way it is. If we had more time, I would have computed all of these things, but I asked you, if you're interested, you can do this on your own if you want to show it for yourself. The way we found all these values past 90 was we created our own triangles, right? We created our own sort of 30, 60, 90 triangles, our own 45, 45, 90 triangles. And we then, so say for 120 degrees, say this is 120 degrees. I said that this would be 60 degrees using basic geometry. And using our 30, 60, 90 triangle, we found that, say the sine of 60 here, that the sine of 120 is equal to the sine of 60. And where did this negative sign come from the cosine? The negative sign came from the fact that this leg here is in the negative direction, right? This adjacent leg. So the cosine of 60 is not just the cosine of 60. Sorry, the cosine of 120 is not just the cosine of 60. You have to account for the fact that this leg extended in the negative direction. So it would be, negative 1 over, so negative 1 over 2. That would be the ratio of the legs. And that's why cosine of 120 is negative 1/2. Right. Okay, so this is what we found. And today, I would like, now that we've sort of established these functions, I would like to play the same games with you that we played with our old functions. Like, we had functions like x squared and, like mx, things of this form, mx plus b. We had functions like e to the x. We had functions like the natural log of x. So now I'd like to play some of the same games, just so you get a sense of how to transform these lines. So what we're going to talk about for the next 5 or 10 minutes should be nothing really new. We're just applying what we know of transformations to these new functions. So what does this 2 do? Anyone? Say I had y is 2x squared. What do we know that the 2 does? Here is my x squared. And we talked a lot about graphing, right, last week. It doubles, it stretches it vertically. Yeah, so Selena, what you said is not exactly specific enough. Doubling sine of x, but
So
okay,
boom.
you're right. Yeah, it stretches the thing vertically.
So I open them.
Yep, so I'll draw my original sine of x, right? Just this nice wave. And I'll work in degrees today for you. Sorry, this is 180, 60. And the 2, what this 2 does, I should do this in a different color so you can see. What the 2 does is it stretches the entire thing. So in a sense, it makes this wave louder, right? It amplifies this wave by a factor of 2. So this used to be the point 1, and now it's the point 2. And this is a good point I'd like to make. Anya and Gabe, 2 of our tutors, have both complained about students not labeling enough points. I think it's partly my fault because I told you that I'm really more concerned with the shape than the numbers, but you need to put at least 1 or 2 points on your graph so we have a sense of scale. Otherwise, there's no way to distinguish between this line and this line if there were no numbers. Okay, Alexis, she told you that. Okay, she was. I actually talked to Anya this morning, so she was like, yeah, these students are not putting enough points. So okay, that was her message and Gabe's message. Okay, how about this? What does this minus 180 degrees do? And I would urge you to think of our earlier examples, like, I don't know, what did this minus 1 do? It shifted this parabola, y is x squared, it shifted it to the right. So what should this 180 do? It shifts it to the right by 180 degrees. And so here, so I'll draw the original function in green, our good old friend. You'll get very used to writing like 90, 180, 270, 360. These numbers will be your best friends. Oops, sorry, that wasn't right. So yeah, so our original function looks like this. And this 180 makes this entire thing move to the right 180 degrees. So it'll look like this. This point here should have gone through 360. Anyway, okay, so I hope this makes sense. It's nice, beautiful. It looks like waves on the ocean, Okay, so this is your final answer. You would not draw this. Okay, great. So you have this sense of shift and we have the sense of stretch. Now let's put this together. What does this look like? Anyone? Let's go swimming in math. Yes. Can anyone tell me what this looks like? There are 2 things going on, right?
To the right 90 degrees.
Yes, very good. So my original cosine graph looks like this. want to make sure I do this right. Okay, there we go. That's my original cosine graph. And now the entire thing gets shifted to the right 90 degrees. And so I'll do that first. So sometimes it helps to draw the points. I'm not the best at visually doing this. Okay, so I shifted it to the right 90 degrees. And now what does this 1/2 do? Yes, vertical compression. And so this point, which was 1, right? This height was 1, that will become 1/2. And similarly, this point, which was -1, will become -1/2. So the entire thing gets squeezed or shrunk vertically. And so this is sort of what your answer will look like. Sorry for my shaky lines, but anyway, I think you got the point. Great. So a little bit of a smoother wave. Okay, how about sine of 2x? So now this is what are we doing? We're dilating the domain, right? So we've dilated the range, we've shifted the domain, but we haven't yet dilated the domain. So what does this do? What does the 2 do? How will it make the graph look? I'll draw the parent function. Someone tell me.
Expands.
It does actually, it doesn't expand. Remember that the transformations on the domain go as the opposite as those transformations for the range. Remember last week when we talked about this and how this was an apparent contradiction? So when this number is greater than 1, it actually contracts. Yes, Aditya is right. Horizontal compression by 1/2. That is correct. And shift right by 90 degrees. No, there is no shift. Well, okay. I think your message was about the last. Okay. Yes, the only thing going on here is squeezing our parent function, which I'll draw here, squeezing everything by a factor of 2. So this 90 will become 45. So, okay, this is where a different color will be especially helpful. This 180 will become 9. Well, sorry, the 180 will become 90. There's no need for me to draw anything. The 270 will become, what is 1/2 of 270? Can someone tell me? Okay, so Selena, squeezing it by 1/2 squeezes it half of 1 and not half of the, no, it's actually it's the latter. It's half of the number it's squeezing. So your latter answer is correct. Yeah, so the entire domain. So literally, 90 will become 45. 180 will become 90. 270, well, what's 1/2 of 270?
135.
Yes, 135. So that'll become here. And 1/2 of 360 is already written. It's 180. So all of these numbers got stretched and all the points that were corresponding. So see how this 90, that this point that was corresponding at 90 degrees, that point gets moved over here. The point that was at 180 degrees, that gets moved to 90. The point that was at 270 degrees, that's going to get moved down here. So every corresponding point, so Selena, I hope this makes sense. Every corresponding point gets moved. And so that wasn't very good. Yeah, that's your new graph. So it has half. Okay, we're about to talk about sort of what this means physically, but you can see it sort of completes its cycle in half the time or in half the distance, depending on what this axis is, that the parent function y is sine of x did. See how it completed its cycle in half the time. So, okay, so I hope this makes sense. And so now I have a question for you. See how these numbers are 90, so we're working in degrees, so you have 90, 180, 270, 360. What if I wanted those numbers to be simpler numbers, like 1, 2, 3, and 4? In other words, what if I wanted my graph to look like this? And here, I'm going to change this to sine because I think sine is easier to work with. What if I wanted my graph to look like this? Can someone tell me how I would transform the apparent function y sine of x? What needs to happen to this function to give me this graph? So I haven't touched anything vertically, but I've dilated it horizontally. So can anyone tell me what the equation for this graph is? Add a coefficient. Very good, Caleb. Yeah, so I need, and you can tell I've left some blank space here for me to do that. And so this is the challenge. What is that coefficient? Well, we know that if you multiply, see, when I multiplied this argument here by 2, that compressed everything by a factor of 2. So if I want this 360, if I want that number to now be 4, what do I need to multiply by? $90, very good. Yeah, so if I multiply my argument by 90, then the 360, so I'll do this schematically. Okay, and I'm going to use colors. I think colors are helpful for people. So 90. And so if my numbers were originally, if my y-axis values were originally, 90, 180, 270, and 360, what multiplying by 90 does, well, that actually divides each of these numbers by 90. And when I do that, I got 1, 2, 3, and 4. See, 90 divided by 90 is 1, 180 divided by 90 is 2, 270 divided by 90 is 3, 360 divided by 90 is 4. So this is very important for you to be able to do, right? Redefine, like fitting your sine and cosine graphs to some desired axis, right? Some desired numbers, like 1, 2, 3, and 4. Here's a more challenging one. I think we'll skip it for the sake of time. But in summary, we've now seen that there are a total of three meaningful transformations, right, that you can do to a sine or cosine graph. We haven't talked about tangent because it's not as meaningful physically. Sine and cosine, we're about to see, are very useful. So what are those transformations? So this is worth writing down because your quiz is related to this. The first thing we did was we saw we could stretch our sine wave or cosine wave by some factor a, and this a is often referred to as the amplitude. So when I said on the first graph, right, we had some parent function, and then we stretched it, and I said that this second wave is louder than the first wave. In a very real sense, it is twice as loud. I think that the dilation factor there was 2. So that wave would be twice as loud. Its amplitude is twice as much as the original wave. So A is the amplitude. This is just a notation, right? Mathematically, it's exactly what we were doing earlier. This is the Greek letter phi, and this is the phase shift. So we saw, like in our, let's see which example, I think the second, yeah, like in this example, we had that cosine, was shifted by 90 degrees. So here our phase shift is 90 degrees. So that is often denoted by the letter phi. And lastly, in this last example, we found that the frequency of the graph, in other words, where it crosses the axis, that can be changed by multiplying by sort of the sort of original scale. And what that does is it divides out, like in this example, it divided out by 90, right? So then you're left with 1, 2, 3, and 4. And so multiplying by 360 degrees times your frequency gives you the desired frequency of your wave. So if I wanted a wave having frequency of 10, okay, and the units of frequency is hertz, for those of you who are not familiar, okay. If I wanted a wave of 10 hertz, I would multiply, my equation would be 360 degrees times 10 t minus phi, and you could write this as, if you were plotting this in a graph or something, that's what this would look like. So what does the frequency mean? The frequency is the number of times your wave cycles through in 1 second. So a 10 hertz wave, if this is 0 seconds and this is 1 second, a 10 hertz wave is going to make 10 cycles. Sorry for my horrible drawing. This is not even 10 cycles. It would be even more. What this is 1 cycle, 2 cycles, 3 cycles, 4 cycles. This was like 5 cycles roughly. So this is like 5 hertz. Anyway, that's what your frequency is. So this is sort of the general way to express a wave. And you'll see this everywhere. And that is where I would like to sort of bring this lecture to, the applications of all of this. And it's very rewarding to discuss. But I want to ask before we move on to that, if anyone has any questions about any of these parameters, the amplitude, the frequency, and the phase shift. Any questions?
No.
No questions. Okay. So the applications are literally everywhere. And it may be hard for you to realize that what you're learning constitutes the very fabric of physical reality. Literally, you're looking at a computer screen or a phone screen, tablet screen right now. The light that is being emitted from the screen and that is entering your eyes, the light is a wave. The signal from my apartment here is being transmitted to you instantaneously. That is a wave. The signal is a wave. Everything we see and hear is a wave. It's really, and the waves are constructed with sine and cosine waves. And most significantly, one of the great beauties of waves is that waves are the solution to these things called the Maxwell equations. And the Maxwell equations are they're 4 equations of physics, very beautiful, profound, deep equations. And their solution, when you solve these equations simultaneously, they give you a wave, an electromagnetic wave. So the electromagnetic spectrum, which includes light, visible light, is just a bunch of waves of different frequencies. So for example, maybe this morning, I just made a bowl of oatmeal and I used my microwave, right? The signals that are being transmitted to your home, those are radio waves, right? Maybe you went to the doctor and you took an X-ray. UV rays, this is where the energy of the sun, the sun emits lots of ultraviolet radiation, and this can be damaging to your skin and stuff. Infrared light is often felt in the form of heat. Like if you have a stove, and you put something on the stove, you might notice it starts glowing red. That's this very end of the infrared. That's the very high energy infrared waves. And then obviously visible light. So anyway, so light itself consists of a wave. And what does it look like? Well, light consists of a magnetic field and an electric field. And so this is definitely not on the SAT. This is just enrichment. And the magnetic field and the electric field are mutually perpendicular. And this is one of the solutions to the Maxwell equations. So this is you can see that I've drawn this like sine, right? So let the red be the magnetic field, which is denoted by B. So B can be thought of as like sine of t, roughly, with some appropriate amplitude and such. And then the electric field is perpendicular to that. And it looks like this. And it is also the sine of something. And so I hope you can tell, I'll draw some lines to make it very clear, that these things are perpendicular to each other. And so light itself, everything you see, and anytime you turn on the radio, this is the information that your eyes are receiving. It's all a wave. And so these things are constructed by, like I said, sine waves, cosine waves. So I hope you can tell that this is like a 3-dimensional plot. Anyway, this is just one of many applications. One profound application was made by de Broglie, who was, this is how you spell his name. It's not pronounced like this. It's a French name. De Broglie found that all matter has some wave-like properties, and he was really interested in electrons and photons and small, things with small or no mass. So Nishan said DNA when I drew this. This isn't really, I can see where you're coming from, but not really. Although it is interesting that DNA was discovered using, I think, X-rays. They used X-ray crystallography to discover DNA because it's, the structure of DNA is too small to see with visible light. So they used waves in this frequency range, here. Anyway, yeah. I can't tell you much about DNA. I haven't taken a biology class in a while. Okay, so de Broglie found that actually all matter has a wavelength. And so in other words, even the Earth itself, even the Earth has a wavelength. You have a wavelength. You have a resonant frequency, so to speak. And this is very, for classical objects, me, you, the Earth, your fridge, your pencil, whatever, your computer, these are all classical objects. And so we can't really detect these wavelengths. They're far below, the wavelengths are far below this thing called Planck's constant, this H, that's what that is. It's a very small number. And so that this limits, this sort of makes your wavelength very small and unnoticeable for classical objects like you and me with huge masses. This is a chemistry, this is a physics thing. No, wait, no, Adi, I said this is not on the SAT. This is for you. This is for your own enjoyment. Okay, but all matter actually has some wave-like properties, and this becomes very relevant for people in quantum mechanics and so on and so forth. So waves actually describe all of reality. All of reality has some wave-like properties, and this is actually something of profound importance, and it's something that ancient people all over the world had some intuition of, right? The many ancient cultures thought of the things that happen around them as having some wave-like properties. They had this notion of periodicity. And one of my friends who's from Japan gave me this definition of music. He said music in Japanese, and this is the word in Japanese for reverberation or resonance. He said that music is best defined as that which reverberates. And it turns out that much of the physical universe is described by sine and cosine waves, like light and sound. Many things in the universe are periodic. Anyway, so this is almost a philosophical point that many ancient cultures have always had this intuition that the universe is constructed by waves. And it's really a miracle that modern science and quantum mechanics has found that, yes, matter itself has some wave-like properties. So anyway, this was really an aside. But for the remainder of this lecture, I would like to talk about actually music, because music is the sum of sine and cosine waves, just like light, just like many other waves, right, that fill our universe. Music is, at its core, just the summation of sine and cosine waves. And that sum is taken in such a way that sounds good to your ears. So I think this will be very enjoyable for people because, so Long said you like jazz music. I do like jazz music, yes. So we're not going to talk about, we're not going to listen to music, but in a sense we will actually. And I would like to demonstrate, so I'm going to share my screen. I would like to demonstrate to you that music is a wave by, okay, let's see here. I'll just share my entire screen. So, okay, so you all can see this, right?
Yeah.
Okay, great. Yeah, it's not amazing. Okay, so I'm going to sing a note, and I'm going to make that note sound as pure as possible. And so it's going to be a high-pitched note, but it's, so if you don't want to hear me sing, then cover your ears. Okay, here we go. Okay, no one laugh. Okay, I'm going to try again. That wasn't that good. Let's find a better note. So what I'm trying to do is replicating. Okay, no one laugh. Okay, no one laugh. Okay, what I'm trying to do is replicate the sound of a sine wave, which is the most pure wave. And I'm going to show you that when I zoom into this wave, look, lo and behold, what did we find? This is this is exactly what I just sang. I've just zoomed in. See, you can see how the seconds are compressed here. 1.9 seconds, 1.915 seconds. So we're, this is like 1,000th of a second right here. So this is on the order of like hundreds of hertz. So I hope this is a good demonstration to you that a wave, that a pure wave is just a sine wave, right? So I'm kind of zooming through it, and you can see, yeah, there there are slight behaviors, there's sort of swells and drops. So there's some other stuff going on, but just, on the course of a few cycles, my voice is really just a wave. I would like to show you something else, and I have a guitar here. I'm just going to pluck a string of a guitar, okay, and I'm going to do the same thing, and I want to see if it gives me the same sound. Okay, here we go. Okay, so that was a little guitar string. Okay, now I'm gonna zoom in here, okay? And we're actually finding that this wave is a bit more messy, right? This is not as pure looking as our friend, the sine wave. See, the sine wave was very regular, but see this wave, it has, it has a big dip and then some smaller dips and then a big dip. So you can see, you can identify one wavelength. Here's one wavelength, right? So what is going on here? Well, what is going on here is that when I've plucked the guitar string, various sounds are heard all at once. Yeah, so what this is a sum of sine waves. And I'd like to show you this very explicitly. Oops. Okay. I'd like to show this to you very explicitly by just literally taking the sum of different sine waves. So I'm going to start with some overarching wave, right? This is a big wave, right? And now I'm going to add to it a smaller wave that has half the frequency. Sorry, that has twice the frequency, half the wavelength. And then yet another wave, and yet another wave. So these are all the waves that I'm going to sum together. And in fact, if you study the nature of a string vibrating, it turns out that all of these waves are simultaneously heard when you pluck a guitar string, just in different ratios. So these are all the various waves that are playing when I pluck the guitar string. And what do they look like when you put them together? Well, I have done that in this line, and they look something like this. And you can play with it by changing the ratios. For example, I can make this number smaller. I can play. If you enjoy this kind of thing, I encourage you to play with it. In fact, you can add a slider here, and you can start playing with the shape. And so the coefficients actually determine the sound of a guitar. And if I compare this wave to my actual guitar wave, it actually looks pretty similar. You can see, there are 3 peaks, right? 1, 2, 3. So anyway, so my point is that a guitar and generally sound can be described very well using waves. Okay, so so I hope this was enjoyable. I would like to make one additional point, and that is, I think I'll have to share my computer sound for you to hear this. But what do these harmonics sound like individually? When you pluck a guitar string, I don't know if you can still hear this. When you pluck a guitar string, it just sounds like one note. But if you were to deconstruct all the different notes, what do they sound like when juxtaposed? In other words, what does this wave, the red wave, what does the red wave sound by itself? How does that sound? What does the blue wave sound like by itself? Right? What does this wave? What do all these things sound like individually? And there is a great little animation, not animation, but demo that I'll share with you. Okay, so I'm going to share my computer sound. So can you all still hear me if I speak?
Yeah.
Yes.
Okay, so this should come through your computer speakers. Okay. So those were the first 16 harmonics. So that's what they sound like, and you might actually be able to hear that they produce a very pleasing sound. In fact, the sound of a major chord with some additional notes. And it turns out that if you study the music of ancient cultures were inspired by this sound. and created music based on those notes. So yeah, so there are some funny notes in there. I hope that wasn't too loud for anyone. There are some funny notes in there, but there are various modes of music. And for those of you who know music, you know, there's the sharp 11 in there. There's the dominant 7. So anyway, point being, okay, give me a sec. Give me just a second. Okay, sorry, dude. I thought the maintenance people had come. That would have been bad timing. Anyway, okay. No, I was not going to cry. Okay, so that's really all I had to cover today. I hope this was somewhat interesting to people. Hopefully some new information. I'm going to send the quiz. Here we go. How do I get back here? Can I play a song for you? Maybe at the end of the course. Yeah, maybe at the end of the course. Okay, so here's the quiz. It's pretty short, shouldn't take long. But if anyone has any questions, feel free to ask.
Is this the quiz from yesterday?
Uh-oh.
Yeah, it's the quiz from yesterday.
Okay, give me a sec, people. Give me a sec. I sent the wrong one. Sorry. Okay. Try that.
Wait, what is the first one?
What is the first one? So we talked about, okay. So we talked about, I'll put it up on the screen again. So are you seeing my screen here?
Me?
Yes, whoever asked the question.
Oh, no, I was asking if it was the first link or the second one.
Sorry. I thought you were like, what is the answer to the first question? No, it's the second link. Disregard the first link. The first link is the quiz from yesterday. I sent it on accident. Yeah, so it's the second link. So I hope today was a bit of a breather for people, sort of hopefully rewarding. Tomorrow, we're going to talk about some trigonometric identities, some of the famous trigonometric identities. So it'll be a bit, today's Wednesday, yes. So yeah, so tomorrow's lecture, as always, will be a bit more abstract, but today was sort of, I think, the rewarding part in terms of the physics of it.
Thank you so much.
You're welcome. Have a good day. You're welcome. If anyone has questions, feel free to ask. See you along. You're welcome, Aditya. I think I will I will end the meeting now. But yes, feel free to attend the office hours. I forgot when they are. Wednesdays. I think Gabe might have office hours. Let's see. Christian has office hours at 1. John has office hours at 6 today. So if you're confused, do attend. Okay, if no one else has questions, I will see you all tomorrow. Okay, see you.